We propose a novel method that optimally computes the relative pose between two frames of a vehicle-mounted camera. The paper is written by Levente, Hajder and Barath. The presenter is the first author. It is a joint work of Eötvös Loránd University and the Institute for Computer Science and Control from Budapest, Hungary, and the Center for Machine Perception from Prague, Czech Republic. The estimation of camera pose between two images is essential for both robotics and computer vision. Our approach assumes planar motion. In this case, the camera is mounted on a vehicle, the image planes are perpendicular to the ground, and their vertical pixel directions are parallel. The main goal of this project is to develop an optimal method for the estimation of relative pose under planar motion. The main application area of our method is machine vision for autonomous driving. For stereo vision, the geometry can be represented by the so-called fundamental matrix if camera parameters are unknown. A general fundamental matrix itself can be estimated from at least 8-point correspondences. For the calibrated case, the essential matrix can be considered consisting of only the extrinsic camera parameters. A general essential matrix can be estimated from at least 5-point correspondences. Planar motion is addressed in our paper. The first specific paper in this field was published by Ortin and Montiel in 2001. They show that planar motion can be written by two parameters and solved it by a numerical method. Other non-optimal solutions have recently proposed by Chow and Wang and Choi et al. The main goal here is to optimally estimate the extrinsic motion parameters. The overdetermined cases are addressed that are essential for accurate model estimation, for example at the last step of a Ransack-like robust method. In stereo vision, camera pose, that is the relative rotation and translation of two images, are usually encoded in the elements of the essential matrix. It can be formed as the product of the so-called cross-product matrix of the translation and the rotation matrix itself. For the uncalibrated case, only the fundamental matrix can be estimated, that comes from the relationship of the essential matrix and the intrinsic camera parameters. If only point correspondences are applied, each location pair gives one equation for the estimation of fundamental or essential matrices. For the fundamental matrix estimation, at least 8-point correspondences should be given. If the cameras are calibrated, only 5 correspondences are needed, as the elements of the essential matrix should fulfill the singularity and trace constraints. The main goal of this presentation is to show how to optimally estimate the pose for planar stereo motion. In this case, the relative motion can be written by two parameters: the rotation around vertical axis, represented by angle alpha, and the direction of the translation, represented by beta. The essential matrix consists of 4 non-zero elements, however, they can be written as functions of the two unknown angles alpha and beta. The estimation for the elements of the essential matrix can be straightforwardly written as a homogeneous linear system of equations, where vector x to be estimated consists of the non-zero elements of the essential matrix. As it is a homogeneous problem, the scale of the solution is ambiguous. We fix the scale by setting the third element of vector x to 1. Moreover, as the first and last two elements of vector x are the sine and cosine functions of alpha and alpha plus beta, they should fulfill the well-known trigonometric rule. The latter fact gives a constraint for the minimization problem. Therefore, there is a linear least square problem for a 4-dimensional vector that contains only 3 parameters, and there is one constraint. Thus, the degree of freedom of the problem is 2. For handling the constraint, a Lagrangian multiplier is applied. The detailed deduction of the solution can be read in the paper. Algebraically, the solution is obtained via the roots of a 6th-order polynomial. The complex root pairs can be omitted. The evaluation for the original cost function determines which roots leads to the optimal solution. Degeneracy is also an important issue. However, it can occur only in very special cases, for example, when corresponding point locations are at the center of the images. For the synthesized tests, ground truth and noisy data are generated by MATLAB. For the camera pose, the planarity constraint is considered. Random points are projected using random camera parameters. Gaussian noises are added to the point locations. The competitor methods are as follow: the 5-point method of Stevenius et al. And the suboptimal 2-point line algorithm of Choi et al. In the left plot, the average of the translation error, represented by angle beta, is visualized. In the right image, the estimated rotational angle alpha is plotted. 3 different Gaussian noise levels are applied. The horizontal axis of the charts are the number of points from which the estimations are computed. The test results are very similar. The proposed optimal method outperforms the rival algorithms as it is expected. The stability of these methods are also tested. In this test, numerical errors are evaluated. The plots show that all the competitor algorithms are stable enough. The less stable is the 5-point algorithm, however, even its stability is good enough. Robustification is also an important issue for pose estimation, as the point matchers often fail. Therefore, the input data for our method are contaminated with outliers. We apply ransack-like robustification. It consists of 2 main steps. First, several minimal pose models are constructed, and the inlier-outlier sets are separated based on the obtained models. The largest set of inliers is selected in the second step, and the model is re-estimated. The proposed optimal estimator can be applied for the second step. For ransack framework, we apply the graph-cut ransack method. We have tested the proposed method on the Malaga stereo and laser U-band dataset containing more than 10 kilometers video. Every 10th frame is selected from the videos, and our pose estimator is run for each consequent images. Point correspondences are retrieved by the well-known SIFT method. As it was mentioned before, the graph-cut GC ransack method requires both minimal and non-minimal model estimators. We have combined several variants as it is written in the table. The first one is the proposed combination. It contains the proposed optimal pose estimator as the non-minimal solver. The baseline method is the 5-point algorithm of Stevenius et al. The method of Choi et al. Is used for the minimal solver for most of the cases. However, it can be also applied as the final solver. The linear solver is a simple method that estimates the 4 unknown elements of the essential matrix as the null vector of the 3×4 coefficient matrix for the linear problem. For the real test, we compute the average of all the tests on Malaga dataset. The cumulative density function is used for the comparison. The obtained rotation and translation are separately evaluated. The latter one is on the left, the former one on the right side. The proposed robust algorithm is drawn by red color in the figures. Its curve is always close to the top left corner of the charts. Therefore, our method is the most accurate robust estimator. The difference is significant, especially for the translation error. In this chart, the cumulative density function of the processing time is plotted. The fastest method are the suboptimal planar algorithm. The 5-point method is the slowest one as it is expected. The proposed algorithm is in the midfield. The summary is as follows. We have shown that the relative pose of a calibrated stereo setup can be optimally computed if planar motion is as shown. For the minimal problem, at least 2-point correspondences are needed. However, our work deals with the overdetermined case. Planar motion is as shown here. That is typical for vehicle-mounted cameras if the vertical translation is 0 and the images are perpendicular to the ground. Our solver is based on a linear system of equations with a single constraint. It can be efficiently solved by applying Lagrangian multiplier. The robustification of the problem is efficient as well. The proposed approach is superior to the state-of-the-art solvers due to the optimality. The processing time is only a few milliseconds. That's all. Thank you for your attention.